Hi guys, welcome to the pre-lab of our flame test. This is a new concept for you, so just try to stick with me. I'm going to explain to you briefly the concept of what you are going to see in the lab tomorrow or Monday, depending on what block you have. But first, we're going to review the Bohr-Rutherford model. So, if you will remember, it has that nucleus on the inside. This is just going to be a model of an atom, not any particular atom. So the nucleus we're just shading in because we're not dealing with the nucleus today. Today we're going to take a look at our electrons and how energy will affect those electrons in that atom. So as you know, you have orbitals around the nucleus, okay? So this is the first orbital. It is named n equals 1 for the first orbital, easy. The second orbital is n equals 2, and so on and so on, okay? I know there's a light there, but that's n equals 2. Okay, now what you're going to do in the lab is you're going to add an ion, or you're going to add a metal ion into a flame, adding energy. So we're going to take an electron. So you guys know electrons go on these energy levels. They're also called orbitals. So right here is an electron, and we're going to, in lab, we're going to add energy. So how are we going to add energy? Well, we're going to add energy in the form of heat, okay? We will have a Bunsen burner, and you're going to have fire, and you will add energy, which is in the form of heat. Energy can also be in the form of electricity. When you add energy into an electron, it's going to get excited. It's going to have more energy. So it's going to increase in energy and go to the next energy level. So then it'll be here. So if you add energy to an electron, it will increase in energy, get excited, and go to the next energy level. It doesn't like that because it's unstable. So quickly it's going to get rid of that energy and go back down to the lower energy level. So it's going to want to go back where it came from, because where it came from is stable, okay? So when it goes back down to that next energy level, it's going to release energy. So when it releases energy, you will be able to see that because it's going to release energy in the form of light. So energy in the form of light. So if you will turn to your textbook on page 92, there's going to be a picture. I'll show you. I'm probably not the best online lecturer, but it's this picture, okay? So you're going to see this picture. Now, I'll just do this. I need an assistant. One of you kids, I'm going to make you be my assistant next time. But anyways, in this picture, okay, this part right here, these are all wavelengths, okay? So these are wavelengths of light. So the only wavelengths of light that we can see with our eyeballs is this tiny little speck right here. This we cannot see, this we cannot see. So for example, we can't see radio waves, we can't see microwaves, we can't see infrared waves, ultraviolet rays like from the sun, we can't see x-rays. That would be creepy though if you saw x-rays while you're in the doctor's office. And we can't see gamma rays. We can only see waves that are between 400 nanometers and 700 nanometers. Okay. So if the energy in the form of the wave is between 400 and 700 nanometers, then you guys will be able to see it. You know that the light or the energy that's being released after this guy goes back down, you know that the wavelength of energy is going to be between 400 and 700 nanometers. So that whole picture that I just showed you, most of that you can't see, the part that's in gray. But the part you can see is called the visible spectrum. So that's what you can see with your unaided eye. When I say wavelength, so in physics you guys may have learned, if you don't take physics, that's okay, you're about to learn it. So you know that a wavelength is that far, okay? So some wavelengths, so for instance, violet wavelengths, they are smaller wavelengths. So smaller would mean that between the peaks, it's less space, okay? Now, if you're looking at the red wavelengths, okay, 700 nanometers, so between the two peaks, the distance is further, okay? So that's all it means when it's talking about wavelengths, is the space between the two peaks, or two troughs, whatever, same thing. So the main point I want you to get is that tomorrow or Friday, so that tomorrow or Monday, you're going to see these electrons get excited because we added energy, fire or heat, and then they don't like it, it's unstable, so they're going to go down to the lower energy level, the stable one. When it goes down, it gets rid of that energy in the form of light. You're going to see it, you're going to record it, and then you're going to write down the wavelength that you saw. Okay, so you're going to see a color. You're going to have like a little chart. You see what color and you see what wavelength you saw. And remember, wavelength is just the length between the two peaks, so how big a wave is. So just remember that we cannot see everything. We cannot see all wavelengths. We can only see a tiny bit of wavelengths. And the wavelengths we see are between 400 and 700 nanometers. Eventually, we're going to learn how do we know what these orbitals look like? How do we know this if we don't have something that can see the whole atom? How do we know what the orbitals look like? So that's what we're going to learn next, is how the scientists used this to find out what orbitals look like. You know, those clouds in the picture in my classroom that I keep referencing to, and you're like so confused. We're going to learn how they figured those out, and then we're going to learn about them.